All right. Welcome again to it's test 5 review. Do I get a Jolly Rancher for catching my own mistake? That's like the mellowest of mistakes I could make though, so we'll live. Alrighty. So MCQ practice. Hopefully we'll split this into MCQ and FRQ and we'll call it a day. And let's dive in. So at a large hospital, the durations of emergency room visits from check-in to discharge are approximately normally distributed. So here's our approximately normally distributed with a mean of 167 minutes and a standard deviation of 76 minutes. Which interval to the nearest minute contains 80% of the durations? All right. So we want to draw a picture. Basically, you should always draw a little normal curve illustrating what you're doing. It helps you establish that you know what you're doing. It helps you establish directionality, and even on a multiple choice question, it will just ground you better. So, we want, with a mean of 167 minutes, 80% of our data to be contained here. So even though this seems a little bit like a confidence interval, it's actually not. What we are going to use here is normal CDF. But normal CDF, actually, we're going to use normal CDF / inverse norm. So because it's normal, and because we have a mean and standard deviation, and we want an area, have mean. That was a terrible mu. We have the mean, we have the sigma, and we have the area. This is a good clue to use inverse norm. Now, in many calculators, when you go to inverse norm, so that second vars, and then you go down to inverse norm, it's going to give you the area to the left of the point. So you have to adjust it a little bit, because if this is 80% in the middle, then we have 20% left, which means since it's symmetrical, we have 10% here and 10% here. So really, we need to find the two values where 10% is below and where 90% is below, because that's going to give us the lower bound and the upper bound. So let's do that. We're going to use inverse norm. The area is going to be 0.10. Let's start with the lower bound. The mu is going to be 167. And the standard deviation is going to be 76. So this is the area, this is the mean, and this is the standard deviation. 10%, 167, and 76. Now, if you have a newer calculator and can just do the center, then you can just make it be 80% and select center. But since not all calculators do that, we're going to go with this. Okay, so this gives us about 70. It's 69.6, so we're going to say about 70 minutes. Now, luckily, multiple choice is a nice thing because only one of these has a lower bound of 70 minutes. To be doubly sure, let's check the upper bound. And we'll do that by saying inverse norm. And this time, if 10% is above the upper bound, then 90% is below. So the area is going to be 0.9. The mean and standard deviation are going to stay the same. And if you have that option, we're still setting it to be left. And we get about 264. And that's wonderful, right? We were able to establish that kind of from the beginning, but never a bad idea to double check in case you did something silly. Cool. Next. An infrared thermometer measures the surface temperature of an object from a distance. The measurement errors for one particular model are approximately normally distributed, with a mean of 0 degrees Celsius and a standard deviation of 1.3 degrees Celsius. If the temperature of an object is 20 degrees Celsius, what is the probability that the thermometer will report the temperature as less than 18 degrees Celsius? Okay, hold please. That sneeze was very concerning to my cat. Sweet. So again, normally distributed. Come on, baby, go. Normally distributed. Temperature of an object is 20 degrees. So 20 is here in the middle. And if there was no error, so the error is what's normally distributed. If there's no error, that would be at 0, 0 error. The error we're interested in is less than 18 degrees Celsius. So it would have to be here at -2, because that's where 18 would be relative to 20. So we're looking for -2, and we're talking about less than 18 degrees Celsius. So we are talking about this area right here. So we want to know basically if the probability of this whole curve is 1, what's the probability of being in that section? If you thought, this seems like a normal CDF problem, ding, 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 congrats you. So we're going to say normal CDF, cumulative density function. The lower bound, we can make -infinity because it's just everything to the left. The upper bound, we can make -2. The mean, we're going to make 0, and the standard deviation, we're going to make 1.3. You do want to be careful. We're not using 20 as our mean, because the normal distribution is about the error, not about the actual temperature. So that's why those numbers are a little different. As usual, we're going to label everything. So this is lower, this is upper, this is our mean, and this is our standard deviation. So normal CDF, that second vars. And upper is -2, mean and standard deviation. Make sure you type things in correctly, like I almost did not. And we get an area or a probability of approximately 0.6197. So 0.061 or 0.62, that's going to be B. The rest of these are too high, and then this one was too low. All right, number 2. Next up, number 3. A study was conducted to test a new style of keyboard in preventing repetitive stress disorders. Volunteers who have had problems with such injuries were randomly assigned to use either a traditional keyboard or the new design. A significance test was conducted with the alternative hypothesis that a smaller proportion of those using the new keyboard will suffer injuries than those using the traditional keyboard. The resulting p-value was 0.07. Which is a correct interpretation of this p-value? Okay. The null hypothesis should be rejected. Well, we don't actually have a significance level. So this is talking about the interpretation of the p-value. It's not talking about what conclusion should be made based on the p-value. So there's a slight difference. So we're not talking about rejecting or failing to reject based on this p-value. We're just saying, what does this p-value mean? So that's not this. This, I'm going to change colors. The null hypothesis should be accepted. That is never going to be your answer. If you pick that, I will cry. You never accept anything. Stats means never having to say you're certain. Accept nothing, and accept nothing less than you deserve. Okay, C. There's a 7% chance that the null hypothesis is correct. Nope, there's a 7% chance of getting a difference between the two groups at least as large as the observed difference if the new keyboard is really no better at preventing injuries. One, it's super birdy, so that's a good sign. Two, that's what a p-value is. A p-value is the probability of getting a result like the one we got if the null is true. It's a conditional probability based on the condition that the null is true. And then here, there's a 7% chance that the observed difference is due to chance. Not chance. It's kind of more like due to sampling variability. It's still not nearly as good as D. So remember, the p-value is if this is your null, and this is the distribution, if the null is true, of all the possible sample values. So this distribution includes some really extreme values, and it includes some values that are not exactly the same as the null, but are close enough that we're like, okay, yeah, this is just random chance. So the p-value is basically the probability of being where you are or more extreme. And if it's two-tailed, it's in either direction. If it's one-tailed, it's just in one direction. Okay, this is really key. If the new keyboard, right? If the null is true, that there's no difference in this case. Okay. Oh, I was going to format this. Oh, well. Okay. For a class project, Charlotte recorded the heights of all 28 students in her class and calculated several statistics. She then realized she made an error recording the height of the tallest person in the class. She correctly had him listed as the tallest, that's important, but needed to add 2 inches to his recorded height to correct it. Which of these measures of spread must remain unchanged? So, mean absolute deviation is the average distance from the average. That's more of like a 7th, 8th grade stats thing. We didn't really get into that. Standard deviation, well, we had data, here, and then we moved this dot. We actually took that dot and moved it out a little further. It was the tallest person. Now it's even more taller. But that is going to affect the standard deviation. That is going to affect the variability. It's going to increase it a little bit. So that's going to change. The variance is just the standard deviation squared. So if the standard deviation squares the variance, if the standard deviation changes, the variance will change. The interquartile range, that is based on the positions, right? Based on the first quartile and third quartile. Those, like the median, are more resistant to outliers or are resistant to outliers. So that's a pretty good candidate. And then last but not least, we have the range. The range is definitely going to change. It was this distance, and now it's this distance. It's clearly going to change. So the IQR is what's not going to change. Onward. Biologists around the world have increased efforts at conservation. Monitoring wildlife populations is important so that appropriate management efforts can be implemented, but such monitoring is often difficult. One study found a cheap and easy way to estimate the number of nesting sites of terns, a type of seabird, by monitoring the number of calls heard per minute. More calls happened when there were more birds, as one would expect. In fact, it turned out that the number of calls explained 71% of the variation in the abundance of nests between breeding sites. Which of the following statements is correct about the correlation between the number of calls and the abundance of nests? Okay. First, let's think big picture. E, we never guess E that we cannot determine or we need more information to determine. If you know exactly why an answer like E is correct, great, you can go for that. But if you aren't sure, if you were blind guessing, you should guess one of these other 4. just as a matter of habit. But we can do better than that. So more calls happen when there are more birds. So as X goes up, Y goes up. So we're going to get a positive slope here. So the correlation coefficient should definitely be positive. Right? So if it's positive, it indicates a positive relationship. If it's negative, it indicates a negative relationship. Then, 71 and 84, how are those related? Maybe some of you are thinking, oh, the number of calls explained 71% of the variation. That is R squared. The percent of the variation explained in Y, explained by the variation in X, is R squared. So now we know that R squared is equal to 0.71. Well, if that's R squared, R is our correlation coefficient. How do we find R if we know R squared? Oh, that's right. We take the square root. So we're going to take the square root of 0.71. And as you might have guessed, it is 0.84. Big takeaway, and the reason I picked this for the review, if you're getting something about a percent explained about the variation, that's probably an R squared value. To find the correlation coefficient, to find R, you have to take the square root. And then you have to think about the relationship to decide whether it's going to be the positive or negative, right? Because this is a squared value. It's always going to be positive. It could have been a negative number times itself and ended up with a positive. So you have to think about, is this a like direct or not relationship? All right, onward. Yeah, I've got 17 minutes and I've got my lesson. All right. A woman who works for a department store wants to sue the company for discrimination based on gender. Oh, no. Her reasoning is that women seem less likely to get promoted than do men. She presented this table showing the employees eligible for promotion divided both by gender and whether they were promoted or not. Does the table provide some evidence to support her claim? Okay. So if promotion is not independent from gender, then the total promotions won't match. So what I mean by that is the total promotions, we had 21 out of 67. So this was total. And as a decimal, that's about 31.3%. So if the percent of women who were promoted is very different from that, then we have evidence of it being dependent, of gender factoring in. And we want it to be independent. We want the percent to match this roughly. So for women, we had 12 out of 43. 12 out of 43. And that's about 0. Sorry, I did this as a percent. That's about 28% or 27.9%. Okay. Those are not exactly the same, but they're reasonably close. Oh, that's lovely. Thank you, Kat. So let's look at our answer choices now. All right. No, because more women than men were promoted. No, that's silly. It's always got to be relative, right? If a lot more women are working there to begin with and more women than men would be promoted, you have to look at the proportions. B, no, because the proportion of women who were promoted is the same as the proportion of men who were promoted. I mean, that's not entirely true. It's a little higher for men. No, because the proportion of women who were promoted is less than the proportion of men who were promoted. Well, that's true that the proportion is less. So just for reference, men was about 37.5%. But that would be a reason to say yes, that the table provides evidence. So this is true, but the no doesn't match it. So that's why this one is out. Yes, because the proportion of women who were promoted is less than the proportion of men who were promoted. Okay. So that's reasonable, and the yes matches the explanation. And then yes, because the proportion of women who were promoted is less than the proportion of women who were not promoted. That should almost certainly be true. So in this case, we're comparing, we're comparing the women's proportion to the men's proportion. Okay. Good. Really, it should be comparing women to total, but whatever. All right. 7. Students in a statistics class, as part of an activity, measured the length of their hair in inches. Summary statistics are shown below. Just to review this, N, sample size. N is always the sample size. The mean, 9.18, median, standard deviation, min, max, first quartile, and third quartile. Then we're asked which of the following statements is true. I am going to draw a quick box plot from this information. So we go, the min is 0, the max is 29. I'm going to go from 0 to 30. You always need a scale. If you don't include a scale in units, you will lose points on an FRQ. I know this is an MCQ, but you should always be sort of thinking about FRQs too. Then let's find where the median would be. So this is about 5, 10, 20, 25. And the median was 3.5 inches. So if this is 5, 3.5 is like here. That's our median. Our minimum was 0. Our Q1 was 2. Our Q3 was 18.5, which will be about here. This is 15, this is 20. And then our max was 29. Someone's got long locks. So here's our box connecting Q1 and Q3. So we can see that it's super right skewed, right? A ton of our data is concentrated over here, and then it's really spread out as we go to the right. We can also see some good benchmarks. So 75% of students had hair at least 18.5 inches long. No, Q3 and up is only 25%. So this is only 25%. This is 25%. This is 25%. And this is 25%. So that's definitely up. My cats think it's dinner time, sorry. 50% of students had hair between 9.18 and 29 inches long. So that's the mean and the max. Especially with a skewed distribution like this, there could be outliers. So we can't say that 50% is between the mean and the maximum. We could say that it's between the median and the maximum, but not the mean. So be careful about that. 50% of the students had hair between 2 and 18.5 inches long. 2 and 18.5. That is true. 50% is between Q1 and Q3 in the box. The distributions of hair lengths can be appropriately modeled by a normal distribution. Nope. All right, it's very skewed. So the median's not in the middle, the box isn't symmetrical. The distribution of hair lengths has at least one outlier. Well, we would have to check the maximum and the minimum. Those would be the only ones we could check. It's probably not the minimum since that's so close to the median and it's pretty close to the mean. But let's check for the outlier just for the practice. So we're going to take the IQR. That's an 8, not a Q. So IQR times 1.5. And then we're going to add that to Q3. And so in this case, our IQR is going to be 18.5 minus 2. So 1.5 times 18.5, oops, minus 2 plus 18.5. When we do that, 1.5 times 16.5 plus 18.5, outliers would have to be greater than 43¼ inches long. Our maximum is not even close to that. So there isn't a high outlier. And again, the reason I'm not checking the low outlier is because Q1 and the median, or excuse me, Q1, the minimum and the median are also close to one another, that it's definitely going to go into the negatives. It's all clustered there at the low end. All right, let's get a couple more done. After graduation, you have the opportunity to open a local pizza restaurant. To cover all of your expenses as well as pay yourself a salary, you need an average revenue of $9,000 per month. Anything less than that and you risk losing your business. You take a random sample of 30 different pizza restaurants, similar to the one you hope to open, and get data on their monthly sales. For the hypotheses, the null being that the average is 9,000, and the alternative being that the average is greater than 9,000, describe a type 1 error and its consequence. Okay, so a type 1 error means that the null is true, but you reject the null. So what this means is this is true, but we think this is happening. We think that, but this is the truth. Okay, so the consequences of a type 1 error cannot be determined. No, the probability of the type 1 error cannot be determined without a significance level, but the consequences we can talk about. So type 1 error, you believe the average sales of pizza restaurants like yours is more than 9,000. So you open a pizza restaurant and have a high risk of losing your business. That's pretty good. We think this, but we're skating on thin ice. Let's check C. You believe the average sales of a pizza restaurant like yours is more than 9,000. So you open a pizza restaurant and have a high probability of a successful business. So that wouldn't be a consequence. That wouldn't be an error. D, you believe the average sales of pizza restaurants like yours is $9,000 or less, so you do not open a pizza restaurant yourself and will miss out on an opportunity to own a successful restaurant. That would be a type 2 error. That would be a we think this, but the truth is that. So that would be the opposite of what we have, or of what we're being asked to describe. So that's not it. This is a type 2 error. E, you believe the average sales of pizza restaurants like yours is $9,000 or less, so you do not open a pizza restaurant because other pizza places are not successful. So that would be a correct interpretation, right? If this is true, then we shouldn't open a pizza restaurant. We should fail to reject, and that's a good thing. We're doing what we should. So that's not an error. Remember, these type 1 and type 2 end with the word error. So the conclusion has to be wrong. So the only option here then is B. Okay. Let's see if we can get to number 10. Ooh. Number 9. A particular crop of one variety of onion has weights that are approximately normally distributed with mean 9.8 ounces and standard deviation 2.1 ounces. How does an onion in the 28th percentile for weight compare to the mean? Okay, so 28th percentile. This is basically an area. So we know the mean is 9.1. And we know that we want the value here where 28% is below. Sounds like an inverse norm situation to me. So we're going to say inverse norm. The area is going to be 0.28. The mean is going to be 9.8. And the standard deviation is going to be 2.1. So this is the area, this is the mean, and this is the standard deviation. When we do that, bloop, bloop, second inverse norm, area is 0.28, mean is 9.8, standard deviation is 2.1. And this, we definitely want a left tail because we want 20th percentile, so everything else is to the left. We get that onion weighs about 8.58 ounces. Now, that is not what the question is asking. It's asking, how does it compare to the mean? So it's certainly less than the mean. So before we even start looking at the actual number, let's cross out everything that says it's above. The 28th percentile is definitely below the mean. Above is wrong, no matter what the value is. Now we can find the difference. 9.8 minus the value we got, 8.58. And we get about 1.22. And I probably could have eyeballed that too, but be precise. Okay. Last but not least, well, for this chunk. Number 10. A pharmaceutical company wants to test a new cholesterol-reducing drug against the previous drug. New drug against the previous drug. If an existing standard of care, existing standard of care is there, you test a new drug against that, not against placebo. You don't want to stop treating people. That's not nice. It does not anticipate much association between cholesterol and gender. So does not anticipate much association between that, but it does anticipate an association between cholesterol level and the amount of exercise a person gets. So we think that this is going to affect things. For a randomized block design, it should. Okay. Block on gender because it is not associated with cholesterol level. No. We want to block on the things that might also be associated because we want to block on the variables that might affect things. Gender, we don't think affects things, so we can knock that out. Block on gender because males and females are different. Again, we don't think that gender is affecting cholesterol much. Block on type of drug? Definitely no. The type of drug is what we're interested in, is what we're testing. We don't want to block on what we're testing. We're blocking so we can make sure we're testing a little bit of both in the different blocks. So we never block on what we're testing. Block on exercise level because it is associated with cholesterol level. That's pretty good. Block on both gender and exercise because blocking on more variables gives more reliable estimates. I would say, and you can probably already tell these questions are not directly from College Board. I would say either one of those is a reasonable answer to the question being asked. Blocking on gender might be called for, especially if this is a large pharmaceutical company with a deep pockets and they can afford to have a block of males who exercise a lot and males who don't, females who exercise a lot and females who don't, and then randomly assign new versus previous drug within each of those blocks. That would be ideal. And the reason we're saying this is it does not anticipate much association, but there could be some, right? If we have to choose between exercise and gender, we definitely want to choose exercise if we can only do one or the other. But if we can do both and create multiple blocks, that would be better because then we could really make sure that we're not getting differences due to gender or exercise levels, that any differences we observe or any statistically significant differences we observe are more likely due to the difference in treatment rather than the difference in the groups. Okay, time for a little break. Hope this was helpful. I'll see you for round 2 in about an hour. But for you, time doesn't mean anything because you're watching this after me doing this. Where's my recording? Bye.